So for example number 5, they're asking us to find the area of the region enclosed by the inner loop of the limit zone r equals to 1 minus 2 cosine theta. First of all, let's have a look at the graph. It's very important that we look at the graphs, otherwise we wouldn't be able to set up the problem, to set up the integral. Alright, so 1 minus 2 cosine graph, and so that zoom fit, and we're gonna have this this graph right here. All right. Well, so notice they're asking us for the inner loop, that is the area of this smaller loop, the inner loop. Okay, but there's issues with this, and you'll see what the issues are. I will show you in a minute. So let's draw the graph real quick. So the issue with this graph is, well, number one, let's find the intersection points. The intersection points. And we do that by setting the function equal to 0, 1 minus 2 cosine theta equals to 0, negative 2 cosine theta equals to negative 1, and cosine equals 1/2. All right. So we're looking for the values for the angles that have a cosine of 1/2. All right, and those two angles are, well, number one, they're both positives, right? Well, I mean, the sine has to be positive, and sine is positive cosine is positive in the first and the fourth quadrant. And those angles are for theta equals pi over 3 and 5 pi over 3. And you can use your unit circle or the triangle approach, it doesn't matter. And well, what are those angles? How are those two angles be represented on our graph? Number one, this ray when we do the loop this way right here, it's going to go like this, right? Here is pretty much the angle in which the loop is starting at, all right? And that's the pi over 3. So once we go around the loop, we end up again at the origin. But that's okay. Yes, that's the point 0, 0. But I mean, in the direction of the loop, it's actually doing this, and that's the 5 pi over 3. All right. But there is an issue here when finding the area under this curve. Well, my picture right here is the one I did by hand. It's not perfect. However, okay, let me look at the one on the graphing calculator. Do you see this area above the x-axis is the same area as the one below the x-axis? You might remember this from Calculus 1. When you calculate areas like this, you're basically adding and subtracting the same area. What would the area be there? 0, right? But I mean, physically there is some area there. So in this case, we have to take a different approach. All right. So instead, we're going to ask ourselves, where are we? When theta equals to 0. For the sake of simplicity, use the angle of theta equals to 0 radians. That is, we're going to plug this in the original function. So r of 0 equals 1 minus 2 sine, or cosine rather. And well, cosine of 0 is 1. So that's 1 minus 2 times 1, which is 1 minus 2, which is negative 1. So when the angle theta is equal to 0, we are at this point, right? At the point where the radius is negative 1 and the angle, well, it's 0. I know it's on the negative x-axis, so it looks like it is at the angle of pi, but no, if you do the trace function on the on the graphing calculator for this particular function, that's the point that we will be at when theta equals to 0 and r equals to 1. So instead, what we're going to do, we are going to find the area of half of the loop and multiply that by 2. Okay, so the area of half of the loop, and let's call this, or let's label this, let's call it R1. Alright, and we're going to find the area, well actually it's the area below, not the area above. So let's find the area below, the one that goes from 0 to pi over 3. Alright, and let's label this R1. Alright, so what we're going to do is multiply or find the area of R1 and multiply that by 2. And well, so let's set up a plan first. Plan. 2 times R1. That's how we will find the area under the inner loop. So in this case, well, we will set up the integral like area equals the 1/2 the integral from alpha to beta r squared d theta. That's 1/2 the integral from 0 to pi over 3 of 1 minus cosine, or rather 1 minus 2 cosine theta squared d theta. Alright, so this one is going to take a good minute to go about because we will have to square the binomial first and then integrate individual term. Well, in fact, we will still have to use trigonometric identities. Well, you'll see. So this will be equal to, alright, equal to 1/2 from 0 to pi over 3, and that's 1 squared, which is 1 minus 4 cosine theta plus cosine, or 4 cosine squared theta d theta. Right? That's only expanding the binomial. And well, do not write 3 integrals yet. In fact, because well, we can integrate 1, that's going to be theta. We can integrate cosine, that's going to be sine. But we cannot integrate 4 cosine squared yet, so we're going to use the trigonometric identity there. So that's 1/2 integral from 0 to pi over 3. We'll open brackets this time, that's 1 minus 4 cosine theta plus 4 1/2 4 times 1/2. Oh, I believe in my notes. Oh man, I forgot. Okay, I will have to. Alright, so that's 4 times 1/2 1 plus sine 2 theta with respect theta. Okay, so this will be 1/2 the integral from 0 to pi over 3 and 1 minus 4 cosine theta plus 4 times 1/2, which is 2 rather, but these 2 distributes with the 1 and the sine to theta, so 2 plus 2 sine to theta d theta. And let's combine like terms for now. Okay, so we have 1 plus 2, which is going to be a 3. Uh, 1 plus 2, that's a 3. And minus 4 cosine theta plus 2 sine 2 theta d theta. Alright? And well, now we can write 3 integrals. So that's going to be 3/2 the integral from 0 to pi over 3 d theta, that's the first integral, minus, okay, this form that multiplies the cosine times the 1/2 outside of the integral will be reduced to a 2, integral 0 to pi over 3 cosine theta plus 2 times 1/2 here, that will become just the integral of sine 2 theta from 0 to pi over 3 d theta. And we may now integrate these three terms right here. Alright, so the integral of d theta, which is 3/2 theta, minus 2 times the integral of cosine, which is 2 sine, and the integral of sine squared, of sine 2 theta rather, that's a negative 1/2 cosine 2 theta. Recall that the integral of sine is negative cosine, and well, we have a mini substitution in there. Alright, and that's going to go from 0 to pi over 3. And well, so let's do upper limit minus lower limit as usual. So that's going to be 3/2 of pi over 3 minus 2 sine pi over 3 minus 1/2 cosine of 2 times pi over 3, which is 2 pi over 3. That's when we substitute the upper limit. Now let's do the lower limit, but this time be careful, because for the lower limit not everything is going to get zeroed out. I mean, for the first two terms is fine. Over here that's going to be a 0 minus 2 times sine of 0, which is also 0, but this is going to be negative 1/2 cosine of 2 times 0, but 2 times 0 is 0, cosine of 0 is 1, times a negative 1/2, it's a negative 1/2, so we're going to have negative 1/2, be careful, that's going to be plus 1/2. The remaining calculation, see how the 3's go away, pi over 2 minus, what's sine of pi over 3? Okay, sine of pi over 3, I believe is root of 3 over 2. 2 root of 3 over 2, and minus 1/2 cosine of 2 pi over 3. 2 pi over 3 cosine, is that negative 1/2, I think? And, well, plus 1/2. Let me move it closer. So that's going to be, well, pi over 2, and that's plus 1/4 plus 1/2. Okay, let me do the calculation below. So that's 1/4 plus 1/2. So that's going to be 3/4, right? 3/4. So minus 2 root of 3 over 2. Oh, actually the roots of 3 cancel, leaving us with simply root of 3. And that's a plus 3/4. And we can combine these three together into a single sum the following way, by just finding the LCD. So that's a 4, 4, and 2, and 2. So that's going to be 2 pi plus 4 root of 3 plus 3. And everything over 4. Alright? Find the area of the region common to the two regions bounded by r equals negative 6 cosine theta and r equals 2 minus 2 cosine theta. And in this case, well, notice these are the same equations from example number 2. So we're going to use info from example 2. Okay? Well, so number 1, let's do the graphs of this. Again, so we can get an idea of what are we going to obtain. So this is negative 6 cosine theta And the other one is 2 minus 2 cosine theta. Okay, graph, and of course zoom 0 so we can see the whole thing. All right. And well, the reason why we're going to use the information from exercise 2 is because we need those intersection points. And remember, those took a while to figure out. Well, we don't want to do that again. Let's just use those points of intersection for the one that was the origin. It was the one that we couldn't find algebraically. We found it graphically, and we got the I believe it's 2 pi over 3 and 5 pi over 3. No, 4 pi over 3. All right. Okay, so let me do a mini graph over here. So this will be like it's actually a circle shifted to the right, to the left, because it has a negative coefficient when it has a radius of 6 actually. And let me do that in like this. And the other one is a cardioid, a sideways cardioid. All right. And well, what are they asking us? So they're asking us to find the area of the region that is common to both. So which area is the one that is common to both? Let's have a look at the graph more closely. Isn't it this area right here? This one is common to both. But again, do you see these issues with the symmetry? We have the same area above the x-axis and the same area below the x-axis. So if we do the area from 2 pi over 3, okay, let me write down those limits of integration, or rather those points of intersection. No, different color. This one was 2 pi over 3, and this one was 4 pi over 3. Okay, those we found them on example 2. Again, we will just use that intersection point. That information. But also we have another issue right here. Now, suppose we can zoom in this picture, and I'm going to focus only on one part of the graph. So this part right here, notice, well, actually I'm going to use a different color. Notice this ray I drew in green right here, which denotes the points of intersection of the two graphs. This gives rise a cusp right here. All right, that means we're going to have some area between the origin right here, this area right here, and a different area past the cusp. So in this case, what we have to do is the following. Do the graph, do the graph of, or the area between that's the area in blue. It's the area. Okay, I know this is kind of weird to see, because when it comes to area under the curves in the XY world, it's always top minus bottom, right? So in this case, we're going to do something similar. So it's only the area under the blue graph right here. Okay, and then from here we're going to add. Okay, so let me color this again. And let me call this R1. Okay, and then we are going to add the area of the sector past the ray from the cusp. But now notice this area is below, or is bounded rather, by the graph in red, in this case the cardioid. Okay, so let me do the same ray, which is the 2 pi over 3 and in this case it will be bounded by that part. Alright, and let's call this R2. Alright. Are you guys following me here about what we're doing? So, and well, that comes again from other very typical problems in Calculus 1 when you integrated the absolute value function, the v-shaped function. Remember that? Well, you cannot just integrate a v-shaped function from whatever limits. You need to consider the graph as both the plus and minus version of the function based on its definition, and in some cases you may need to split it into two integrals. That's exactly what we're doing here, but in the polar world, in a situation in which we also have this cusp right here for which we need to cut the area into two essential pieces. But notice something, we're only setting this up for the upper part of the area, because if we include twice the area, well, again, we're going to get a 0 as an area, and clearly that area is not 0. So instead, the plan here, that's going to be 2 times R1 plus R2. Alright? That will get the area of the above part, and by multiplying this by 2, taking advantage of the symmetry property, we get the total area. So let's see, let's set up and okay, I'm going to write, okay, never mind. Okay, so 2 times R1, that's 1/2 the integral from pi over 2 to pi over 3. Where did I get that pi over 2 and where did I get that pi over 3? Well, so this is right here in green. When the circle in blue touches the origin, or rather the pole, it's actually doing it with this angle, which is pi over 2. Alright? It's not 0. Yes, even though it's the origin, but it's actually getting to the origin vertically, as opposed to the cardioid. Do you see how the cardioid instead it's hitting the origin horizontally, not vertically? That makes the whole difference when it comes to defining limits of integration. I understand this is a little bit tricky to see. It's not, it's not as straightforward as seeing limits of integration in the XY world. All right? But hopefully what we're doing here makes sense. So in this case, well, the the graph in blue which is -6 cosine theta quantity squared d theta. I'm not gonna have enough time or enough space. Now I will. Plus the area for R2, and in this case R2 will be 1/2 the integral from pi over 2, and no, not pi over 2, actually 2, it's pi over 3, or no, not 2 pi over 3, 2 pi over 3 to pi, which is the negative horizontal axis. And in this case, oh my god, you gotta be kidding, 2 minus 2 cosine theta squared. Okay, well, let's simplify. Well, let's distribute the 2 so we can get rid of one of these 1/2 factors. So that's going to be simply the integral from pi over 2 to pi over 3. That's 36 cosine squared theta d theta, plus 2 times 1/2, the 2's cancel, and that's going to give us the integral of 2 pi over 3 to pi. And let's square this binomial. So that's going to be 2 squared, which is 4, plus 2 times 2, which is 4. That times 2, that's negative 8. Cosine theta plus 4 cosine squared theta d theta. I know this problem is really going to take maybe not as much as it seems. So what I'm going to do to have a better organization here, how about we label this as I1, I2. Notice this is no longer R1 and R2. This is just I1 and I2 to denote the result of the integral 1 plus the integral 2. So let's do one at a time. I1. The first integral, that's the integral of pi from pi over 2 to pi over 3. That's to pi over 3 rather. I keep making the same mistake. Sorry about that. Okay. And well, that's 36. Let me write the 36 outside. And well, we have a cosine squared. We cannot integrate cosine squared just the way it is. So we have to use a trigonometric identity. 1/2, 1 plus cosine 2 theta d theta. That's going to be equals to 36 over 2, which is 18. Integral from pi over 2 to 2 pi over 3 of 1, or just d theta, plus 18 integral of cosine 2 theta d theta. Alright, and we can easily integrate these two terms. Well, the integral of theta, of d theta is theta, 18 theta, and the integral of cosine, which is positive sign, but we have a 2 theta, that's 1/2 that, well, 18 times 1/2 cosine, or rather sine, 2 theta, and that going from pi over 2 to 2 pi over 3. Let's reduce the 18 over 2. That's 18 theta plus 9 sine 2 theta from pi over 2 to 2 pi over 3. This will be equal to 18 times 2 pi over 3 plus 9 sine of 2 times 2 pi over 3. Be careful with the coefficient inside of the angle. That's 2 times 2 pi over 3. So that's evaluating the upper limit using the fundamental theorem of calculus. Let's subtract the evaluation at the lower limit. So that's 18 times, yes, unfortunately nothing or not much will be zeroed out over here, so we'll have to write everything, and that's plus 9 sine of 2 times pi over 2. Yeah, this one will get zeroed out. Okay, so number 1, 18 over 3, that's 6. 6 times 2, is that a 12? 12 pi. And okay, this is going to be 2 times 2, that's 4 pi over 3. Sine of 4 pi over 3, I think, is negative 1/2. Is it? Yeah. Negative 1/2. Well, I think I have something different. I got, no, it's opposite over hypotenuse, negative root of 3 over 2. So plus 9 times negative root of 3 over 2. Okay, and then minus 18 over 2, that's 9, so that's minus 9 pi, and this is sine, this term is the only one that's going to go to 0. Okay, that's the only one that goes to 0, plus 9 times 0. Alright, let me make this look like a 0. Perfect. So we're going to end up with 12 pi minus 9 pi. How many pi's is that? Is that 3 pi? And minus 9 root of 3 over 2. All right. So that's the answer only for the first integral. Questions about the first integral? Let's have a look at the second integral, I2. So for I2 we said, okay, the integral from 2 pi over 3 to pi of 4 minus 8 cosine theta plus 4 times, how about that 1/2, 1 plus sine, no, cosine 2 theta. Okay, let me highlight what I just did. So to avoid just rewriting the whole thing again, I'm rewriting this cosine squared theta that we got in the original setup, in the initial setup, and I'm replacing that cosine squared theta with its corresponding power reduction trigonometric identity. Alright? Before we can split this into a few integrals actually. Alright, so number 1, that's 4 over 2, that's going to be 2. This will be a 2. Oh, come on. Okay, this will become a 2, and these 2 will be distributed over here, over the 2 terms. So this will be the integral of 4 minus 8 cosine theta plus 4 over 2, which is rather 2, plus 2 cosine 2 theta d theta. And then the whole thing goes from 2 pi over 3 to pi. Alright. Let's combine like terms in the same way that we did before. That's going to lead us to the following. 6, the integral of 6 minus 8 cosine theta plus 2 cosine 2 theta d theta from 2 pi over 3 to pi. And again, 3 integrals right here. We may go about to split them into 3 smaller integrals. That's the integral from 2 pi over 3 to pi of 6 d theta, or rather, let me take the 6 outside, minus 8 integral of cosine of theta d theta 2 pi over 3 to pi, and plus 2 integral of cosine 2 theta d theta from 2 pi over 3 to pi. Alright, so the integral of theta, of d theta, it's theta, that's a 6 theta, minus 8 times the integral of cosine, which is sine, and then plus 2 times 1/2 the, well, because the 1/2 comes from integrating mini u substitution, so that's going to be sine 2 theta, and then the whole thing from 2 pi over 3 to pi. Cancel the 2 with a half, and that's going to be 6 theta minus 8 sine theta plus sine 2 theta from 2 pi over 3 to pi, and just the same way we did it before. I mean, fundamental theorem of calculus, evaluate at the the integral at the upper limit minus the evaluation at the lower limit. So this will be 6 pi minus 8 sine pi plus sine 2 pi. Well, some terms are going to get zeroed out, not all of them. And then minus 6 times 2 pi over 3 minus 8 sine 2 pi over 3 and plus sine of 2 times 2 pi over 3. Alright? Okay, let's do the calculations for each of them. Let's see. Okay, number 1, sine of pi. That's going to go to 0 because the sine function has the zeros at pi or multiples of pi. Sine 2 pi, well, that's also, for the same reason, is going to go to 0. And well, sine of 2 pi over 3 and sine of 4 pi over 3, well, those are going to require their standalone calculation. So we'll see about that. So that's a 6 pi right here that survives. 6 pi. And then minus 6 times 2, which is 12 over 3. Is that a 4 pi? But that's minus 4 pi. And well, what is... Oh, minus will be plus 8 times whatever sine of 2 pi over 3. Sine of 2 pi over 3 is that root of 3 over 2. And negative times a positive, that's going to be negative sine, or sine of 4 pi over 3. Sine of 4 pi over 3 is that a negative, be careful, negative root of 3 over 2. So we're subtracting the quantity, and we're also getting a negative quantity out of evaluating the trigonometric function. So be careful with the signs right here. So minus becomes a plus. All right? So anyway, yep. Let's keep combining this together. We're almost done with this exercise. So 6 pi minus 4 pi, that's 2 pi. And well, what's 8 over 2? Isn't that a 4? 4 root of 3. And minus is plus root of 3 over 2. And let's use LCDs back again. You know what? I'm not going to reduce. Instead, I'm not going to reduce this because it's easier to just go 8 halves plus 1 half. Isn't that 9 halves? Really? Alright, so that's our final answer for I2. Alright, let's go back to the original problem. Yes, we're almost there. So recall from the very beginning of the problem we set area to be 2 times R1 plus R2. But once we computed R1 and R2, we reset up this problem as I1 plus I2. Which in this case is the result of combining the result of I1. For I1 we got 3 pi minus 9 root of 3 over 2 plus the value of I2, which in this case is 2 pi plus 9 root of 3 over 2. And the good thing here, cancel those numbers, 3 pi plus 2 pi. Isn't that final answer? Yes.
Did we double it already?
Yeah, we already doubled it at the beginning. Yes. So when we set up the integral as R1 plus R2, we multiply that by 2, and then when we divide that by 2, so what we did here is distribute. 2 times a half is just a single integral. The other 2 times a half, they reduce. And then we just rename this as I1 and I2. All right. So